This is the lesson for section 8.1, which is on Lewis dot structures and the octet rule. And you can see that our goals today are to learn the octet rule, label our periodic table so that we can quickly get the number of valence electrons, and also represent atoms and ions with Lewis dot structures. So before we get into all those parts, we need to start out by defining valence electrons. We talked about it last chapter, but these are the electrons that are in the highest energy level. We would also say that they have the highest principal quantum number. So we could ask the question, how many valence electrons does bromine have? And the best method for coming up with that number, if you don't know, is to write out the electron configuration. So pause the video, write out the electron configuration, and we'll continue. Now that you've got the electron configuration, compare it to mine, and you can see that the two underlined sublevels, 4s and 4p, both in the highest energy level, which is energy level 4. And remember that those superscripts represent the number of electrons. So adding up 2 and 5, we get 7 valence electrons for bromine. Now we could repeat this for any element on the periodic table, and there's a shorter way to do that. So at this point, if you would get out your periodic table, we're going to make some labels to it. You'll notice that we'll be labeling groups 1, 2, and 13 through 18. When you have your periodic table, go ahead and continue the video. Now that you have your periodic table, you can see that I've marked in green the number of valence electrons per each group. So these are for the atoms where the element has the same number of protons and electrons. So in group 1 there's 1 valence electron, group 2 has 2. The transition metals that I didn't talk about, or I didn't label, generally have 2 because of the 4s or 5s or whatever their outermost s orbitals are. On the other side, you can see that the numbers just continue to go up, so 3, 4, 5, 6, 7. The last group with helium, remember that helium, in order to fill its octet, or fill its electron configuration, it's only going to need the configuration of 1s2. So that means 2 electrons only. So we say that 2 valence electrons for helium. For the rest, it's 8 valence electrons because of filled s and p sublevel. So the next thing we'd like to do once we can count the number of valence electrons is start to represent something called a Lewis dot structure. And this is our lead into bonding. And so you can see what our steps are. We'll start out where we will write each symbol, and then for each valence electron that we identified for that element, we'll place 1 dot around it. And these dots are placed on 4 sides, kind of like a square, and you normally put 1 dot on each side of that square until you end up with a 5th. And then from the 5th, 6th, 7th, and 8th electrons, you start to pair the dots. Take a moment, pause the video, and copy the notes for the sample Lewis dot structures for period 3 up at the top, as well as the octet rule and those 2 special notes. Once you're done, we'll continue the video. Okay, so notice that for our Lewis dot structures that we're placing 1 dot if that element has 1 valence electron, 2 dots if it has 2. The exact placements of where I had put these dots is not as important as the fact that I wasn't pairing dots until I started to reach 5 with phosphorus here. So I could have put the sodium dot on the other side. I could have put a magnesium dot on the other side. That's really not as important. Now the octet rule is very closely related to these Lewis dot structures, and the general rule is that atoms tend to gain or lose electrons until they have 8 valence electrons. Nonmetals tend to gain electrons because they have high numbers of valence electrons, and metals tend to lose electrons to obtain an octet by losing their valence electron shell, and then the previous core electron shell becomes the valence shell, and that has 8. So in general, we would say that the atoms will change as little as possible in their number of electrons in order to reach that octet. For instance, phosphorus, which you have written down as an example, is going to gain 3 electrons more likely than it would would lose 5 electrons. The other part that you need to know about is that the very smallest atoms, and especially we would focus on hydrogen, will tend to only take on as many as 2 electrons in their valence shell because they all will fill out the 1s orbital only, that first energy level. So just remember that hydrogen will never go over 2. If anything, it'll lose all of its electrons and just have 0.